Okay, off we go. So last time, here's what we were talking about. And I'll tell you what, I'm going to rewind. I'm going to go full screen, and then I'm going to, let's see here. I think I can do this. Here we go. So this was the kind of the framework that I had set up. And it's abstract and seemingly sort of like, what's the point? This seems like unnecessary for, abstraction and silliness in a way. But we're about to make massive use of this framework, right? So the idea is to, once you realize that you have an accumulating quantity, to make a sequence of connections. First of all, when you have an accumulating quantity, you can think of that as being kind of like a stuff. Oh, I'm in the wrong mode. There we go. Kind of like a stuff. Now, it doesn't have to be a stuff. To think of it as being a stuff, as being a kind of a substance, It behaves like a substance. So why not think of it like a substance? It's great intuition. It's very relatable. And it will always lead you in the right direction when you have an accumulating quantity. Okay. Once you realize that you can think of it like a stuff, it behaves like a stuff, well, stuff has an associated density. If you have a stuff, you can talk about stuff per unit size. Volume, area, whatever the natural notion of size is. So we have these associated densities, and again, we don't normally think of work as being a substance, but if we pretend that it's a substance, then I can talk about how much of that make-believe substance is there per unit size. And once you have a notion of a density, then you can start writing down these kinds of theorems. And again, it seems a little bit weird. What's not weird to think that mass is the sum of the little pieces of mass, and that mass is density times area. That's highly relatable. When you say the same thing for work, it starts to seem a little bit, wait a minute, is that a bunch of nonsense? Can you do that? And the point to all this development is, yeah, you can. You don't have to, but you can. Right? All right. So, reminder then, let's see here. So back to where we were with developing Green's theorem, we made the observation, kind of deep observation really, that boundary circulation. You give me some region, you give me a region D, we can talk about what is the boundary of D. That boundary is an oriented curve, of course, oriented according to certain rules. And on that oriented curve, we can talk about the vector line integral of a given vector field, and again, we call that circulation. So this construction, totally non-physical, right? This is an algebraic computation. It's not physical at all, but it's an accumulating quantity. And so again, this is where it starts to get a little sort of, can you do that? Because it's an accumulating quantity, I'm going to view it as being a kind of a stuff. I'm going to talk about its associated density. And then I'm going to write down a corresponding integral calculation that we're going to call an integral theorem or a density theorem or an accumulation theorem or whatever you want to call it. Okay. All right, so here we go. We've got our accumulating quantity. And by the way, then this picture up here is just for fun, but this is a nice little exercise. So we saw how in this picture what happens on the sort of the shared interior, sort of shared boundary edges like this, that you end up with that same edge twice, but with opposite orientations, and they cancel. And this is just an observation that it doesn't matter how many pieces you cut it up into, there's always going to be. I'll just zoom in just for fun. I can get this thing to there we go. If I were, for example, to look at this edge, well, thought of as part of the boundary of this region, it's oriented that way. And thought of as part of the boundary of this region, it's oriented that way. Same edge, opposite orientations, they cancel. Right? And the exact same thing is going to happen on every one of these interior edges. They all cancel, and the only edges that are left are the ones that are not interior edges, namely boundary edges of the whole. And so just like in the previous example, it's an accumulating quantity. Chop it up however you like. Okay, so that was just kind of a fun little digression. But so we've established this as an accumulating quantity. If it's an accumulating quantity, it behaves like a physical stuff. If it's a physical stuff, you can think of it as having a corresponding density. Again, super weird because of boundary circulation, it's not a physical thing, but we get to pretend that it is. And if it has an associated density, then we can compute the quantity of it as an integral of that density. Again, we're just doing this that we set up previously. Any accumulating quantity. Okay. All right, so now I am going to skip the calculation that tells us what the density is. The corresponding density, keeping in mind that our quantity is circulation. The accumulating quantity, the thing that we're thinking of as a stuff or a substance, is boundary circulation, which I'm just going to call circulation. Boundary hopefully will be implicit from here on out. Circulation density, you can compute it. It's not even that bad of a calculation. It's in the book if you want to see it. It's important from a mathematical point of view because, it's part of what makes it work. And but for our purposes here, it's tedium. It's mostly just tedium, right? So I like to just skip to the punchline, and the punchline is wrong color. This is the formula right there. It's dq dx minus dp dy. Whatever your vector field is, right? If the vector field whose boundary circulation you're talking about is p comma q, that p, it goes there, that q goes there. Easy little calculation. We've got a formula for density for boundary circulation thought of as a stuff because it's an accumulating quantity. All right. Now, before we put it all together, we've got everything we need. All the pieces are on the table. We just have to build the Legos, right? So before we do that, let me just talk a little bit about notation and terminology. I hope that you will view this expression right here, primarily the thing that you're computing when you write that down and compute it. This is how I want you to think about it. I want you to think of that as circulation density. I want you to think of boundary circulation as being a stuff. I want you to think of this as being the associated density. That's for intuition. Now, how are you going to see it in practice? How are you going to write it down? The most common way to write this down is to call it curl. Y'all will remember that from back in chapter 3, I guess it is. Right? We talked about curl, and I made some hand-waving statements that what curl represents. Well, it has something to do with how the vector field is kind of rotating around. To what extent does that represent sort of an element of rotation? And we had to do a lot of hand-waving and stuff. This is why. It's literally computing boundary circulation. We've talked about how circulation literally means the extent to which the fluid is going around in circles. But specifically, the density, how much of that is happening near a given point per unit size. That's literally what curl means. So that's why that intuition kind of makes sense. Now, some other notations you should be aware of. I think this one actually is underappreciated, calling it rot, short for rotation, right? Kind of the same basic idea. Just from a semantics point of view, I feel like rotation is a bit better description of what we're really talking. We're literally talking about the extent to which the fluid has kind of a rotational element to it. Curl suggests something stationary that's curling, right? I feel like the rotation, I don't know, this is just, to my intuition, rotation's a little bit more on the nose. But it's a less common notation, and couldn't tell you the history on that, but for whatever reason, doesn't come up as much. Curl is the more common one. You may recall way back when we talked about this thing called the wedge operator. This is back in chapter 1. This was in the section on cross products and determinants. And wedge kind of, in a lot of ways, is kind of like a two-dimensional version of cross product. Again, in certain ways, and it's not exactly the same, but it's got certain of the similar features. So as it turns out, and this is a nice little micro exercise, if you compute the wedge product of the del operator, the two-dimensional del operator, and a vector field f, p comma q, in fact, you get curl. So this is another notation that you can use, and some people like this notation. It's not super common, but it's just reasonable. I like to think of this as being this, I like to call it Green's operator. It is the operator that makes Green's theorem work. We're about to write down Green's theorem. Sort of, again, I'm procrastinating. We're right on the 2-yard line. We're going to run it into the end zone in just a second. We're going to have this thing called Green's theorem, and this is the thing that makes it work. So to me, Green's operator seems like a reasonable terminology. And then I just my own personal notation. To me, GRN is an easy little abbreviation suggesting the term Green's operator. This is not very common. You will see GRN on a lot of my old exams. And then at some point I decided, all right, I'm trying to persuade a planet to change their notational preferences. This is probably not going to happen. So I kind of gave up on it. But anyway, on my old exams, you're going to see GRN. It just means curl. It's just a different notation. In the book, you will see this notation, which I, in fact, very much don't like. I think this is a problem. We're looking at a two-dimensional vector field here. We have a two-dimensional del operator. When you have two vectors in 2 dimensions, there is no cross product. That doesn't make any sense at all. The reason they write it like that is because if you were to pretend that the vector field p comma q was actually p comma q comma 0, and then compute del cross in 3 dimensions, thus resulting in a vector which you would then dot with the 0, 0, 1 vector, that you get this formula. Right? So, I mean, it's not that this doesn't make any sense at all, but it requires some deliberate misunderstandings that I just don't see where the payoff is. Right? Why is that notation better? We already have a long list of options. I just don't see any benefit to that at all. So I'm going to say, please don't use this notation, but be prepared that you will see it in the book. Anyway. Okay, so let's run it into the end zone now. And just a quick reminder, this is the plan. We have an accumulating quantity. We think of it as a stuff. It has an associated density. We've got the formulas for our associated density now. And now we're just going to write it down that the whole is the sum of the parts, and the parts are densities times size. I'm just going to write this down. And here it is. Nothing to it. Our accumulating quantity, not mass, circulation. It's an accumulating quantity, behaves like a substance. We're going to treat it like a substance. This is the thing that's playing the role of mass in the little integral theorem that we're about to write down. And again, the whole is the sum of the parts because it's an accumulating quantity. And on any given little piece, oh gosh, let's see here, color choices. On any given little piece, stuff is density times size. And again, curl is that density. So there's our final punchline. Now that when people write down Green's theorem, they tend to write it down as this integral equals this integral. Which it is, yeah, sure, absolutely. That's how we're going to use Green's theorem. We're going to most of the time we're going to use Green's theorem as, hey, I need to compute a boundary circulation. How am I going to compute that boundary circulation? Oh, hey, check it out. I can compute a double integral of curl, and very often this is a super helpful computational tool. In practice, that's how we're going to use it. Right? It's an alternative integral to help us compute what might be a difficult integral. But the thing that makes it work ultimately, deep down, the big point is that circulation is an accumulating quantity. Okay. All righty. By the way, don't forget when you write down a vector line integral, there's various different notations for vector line integrals, and I'm constantly weirded out by the fact that when people write down Green's theorem, it's one of the moments where it is most common to see the vector line integral written in coordinate form, and so you'll see this written as integral of p dx plus q dy. And it's just, again, it's just extra bulk. I don't see the advantages of writing it that way, but it is very common to write it that way when you're writing down the theorem. So heads up, you're going to notice that. Okay, let me pause I've got a couple of examples set. But before I go on to the examples, is everybody with me? Is everybody on board? Yeah?
What do you mean by no singularities?
Oh, yeah, I've got an example coming up. We might not even get to it today, but so the theorem is a delicate theorem, and everything does have to, I don't want to get into the weeds of the formalities, but it does turn out that if there is any problem, if the vector field fails to be defined somewhere, big problems happen. And so, yeah, we'll get to that. Good eye, and I appreciate you checking up on it. So probably tomorrow. Probably Friday. Right. Okay, we've already talked about this, that the way you should think of Green's operator is it's a sort of a measure of locally how much the fluid is rotating. Okay, example. We're going to compute this integral. It's a vector line integral. Our curve is the clockwise oriented unit circle. Our vector field is this fairly unfriendly looking vector field right there. It's got a tan in it, right? Calculations that involve tan. Oh my gosh, and we're going to have to do an integral that has tan in it. This is not looking super friendly. Okay. Now, real quick, what's our sort of pre-existing default way to do this? The pre-existing default is, you want to compute a vector line integral? Parameterize that curve. And let's just think a couple of steps down that road. How do you parameterize this curve? Clockwise oriented unit circle. Well, sines and cosines. X and Y are sines and cosines. That means that the vector field, when I do the pullback, the x's and the y's will be sines and cosines. So super weirdly, this is going to be tangent of another trig function, right? So super weird integral, right? Not looking like a good way to do the problem. Okay. Next thing to notice. All right, so we want to compute a vector line integral, but wait a second, it's better than that. That curve, the curve over which we are computing a vector line integral, is a closed curve. So this is a circulation. This is not just a random vector line integral. This is a circulation on a closed curve. Hey, wait a minute. We have a theorem about how to compute circulation on a closed curve. If you want to compute a circulation on a closed curve, apparently we can just write down a corresponding double integral. Who knows? Maybe that'll be easier. By the way, this is not a magic wand, right? This is a tool that works sometimes. Sometimes when you have a hard circulation to compute, sometimes the corresponding double integral is easier. Sometimes it's not. But sometimes it is. So that's why this is a good tool. But sometimes it's not. So that's why I say it's not a magic wand. Okay. All right, now, cool. So we are optimistic this is going to work out. We've got a curve. The curve is a closed curve. Let's look at our theorem. Does the theorem say that I can use this for any closed curve? And tragically, it does not. It's not quite what this says. You're going to notice here what this says is it's got to be more than just a closed curve. It has to be a boundary. This is a big deal. It's got to be a boundary. After all, it's for the construction of boundary circulation that we do this computation. We're assuming it's a boundary. This formula here requires that it be applied to a boundary. And boundaries, again, strict term. You got to worry about the little detail devils and ways, which way is it going. Orientation is a big deal here. So, okay, we have to think about this then. Is this curve, why did I just remove that? That's exactly what I wanted. That curve, clockwise, unit circle, is that a boundary? And I'm sorry to report, no, it's not. Doesn't follow the rules. Rules are very important. Everybody with me so far? It's not a boundary. That's so close. Oh my God, so close. It's just off by the orientation, right? I mean, if I were to look at the same exact curve, same exact underlying curve, but just oriented in the other direction, C minus, in other words, right? C minus is a boundary, literally, orientation and all good, right? So I can apply Green's theorem to C minus, even though I can't apply Green's theorem to C. Everybody with me? Yeah.
Wait, how do you know that it's not a boundary?
Because it's not oriented correctly. Yeah, and so remember we have these strict rules about orientations, and you have to go such that the region's on your left, and as I go in the direction that the green curve,
Right.
it's just not. Yeah. Okay, so here's how we deal with this, and it's ultimately no big deal. I just recognize that the integral that I'm interested in is related to the integral around the opposite oriented curve by way of a minus sign. It's that minus sign. It's just the fact that we're oriented in the wrong direction. And as soon as I say, well, this, I've put in that minus sign, now I'm looking at C minus, and I can immediately recognize, oh, well, C minus is a boundary, and if you're looking at a boundary circulation, boundary circulations, I can apply Green's theorem. And of course, don't forget to carry that minus through as well. How are we doing? Is everybody on board? Okay, so now we've transformed our question. Let me just get rid of the mess. Here, now I just need to compute, minus sign and all, but I need to compute a double integral of curl. Okay, we're going to have to compute curl. Okay, fine. So I've got to take my vector field here. I've got to compute curl. How do we compute curl? Okay, well, let's remind ourselves here, way back up to here. Curl, aka root, aka blah, 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 blah. Thought of as circulation density, the integrand for our integral theorem. Here's our formula, dq dx minus dp dy. Plug and chug. Partial derivatives, right? Nothing to it. And if you do so, you will find that curl, well, here's my q. The x partial of this q is 3. Here's my p. The y partial of that p is 1. 3 minus 1, 2. Constant. Convenient constant, no less. And so was this a worthwhile exercise? Did I help? Right? We had this integral where I was looking at my vector field. Oh my gosh, this integral, if I do the usual pull back through a parameterization, yikes. It's going to be ugly. We've transformed instead now by using Green's theorem to a double integral. And what do we think? Is this an easier double integral or harder? I think this is way easier. If the integrand's a constant, the domain is a garden variety geometric figure, right? The unit disk. This is the world's easiest integral, and we're done. Everybody see how that works? That's in practice how we're going to use Green's theorem as a computational tool. Here's another example. Now this one's a little bit weirder. Oh, I'm sorry, question, yeah. Oh, well, there were two questions, but you first, then you. Go ahead.
I'm sorry. For when we take the curl,
Yep.
For dpdx, why do we use the y coordinate?
It's dq dx minus dp dy. Yeah, so the little detail devils, you do have to make sure to remember. Yeah, is that cool? Okay, yeah. And you had a question as well?
What about the bounds of d? Like, are we using like the unit circle bounds?
Oh, yeah. It's the unit disk, right? So let's see. Let me go back to the thing. So our original curve C is this. The domain D for the double integral is the thing that, other than the orientation, it's the boundary of. It is that unit disk, like that. It's that two-dimensional region. Is that cool?
Can you mention like what actually you use for the range?
For the domain?
For the domain.
For the double integral?
To the computation with the domain.
You're talking about D.
Yes.
D is the unit disk.
What's the domain of D so we can actually compute?
D is the domain. So remember, if you have a double integrals are defined on a two-dimensional region called the domain of the double integral. And I'm saying this two-dimensional region, the unit disk, that is my...
The computation in the last steps.
The what now?
The computation in the last steps.
Down here.
Yes.
Yeah, the D is it's the unit disk. So I'm computing over this unit disk. I'm doing an integral, and the integrand is 2, and I'm computing this double integral over that unit disk. Is that cool? Yeah. Okay. All right. Okay. Let's see another example. So this is a weirder example, and we're going to have to be a little bit more careful with orientations here, but ultimately it's going to be basically the same ideas. So you'll notice our curve is sequence of line segments, right? It's like this, and then that, and then that, and then that. That's our domain for our vector line integral. And again, we're computing a vector line integral over that curve of this given vector field F here. And again, well, you can do this the old-fashioned way, but it's 4 separate curves. You're going to be computing 4 separate vector line integrals. None of which are particularly hard, but there's just a certain amount of tedium of you're going to have to parameterize each one of these line segments, and then you're going to have to do, an easy vector field, but still there's just, oh my God, a lot of little details to be done there. So here's a much better way to do it, and that is to reconceive of our domain as being made up of these 6 line segments. Does all the same stuff. But then I can think of what I have on the left. Let's see here. Let me color code this. I can think of these as being the boundary of that gray region called D1. And then I can look at what remains here in light blue. That, my gosh, it's I'm going to say it's the boundary of D2. Oh, wait a minute. No, it's going the wrong direction. So again, I have an orientation problem. And so, okay, opposite orientation of the boundary of D2. Is that cool? So, yeah, okay, well, so then, having broken it up like that, and keeping in mind that minus sign causes a minus sign on the value of the integral. Now I have a couple of boundary line integrals, and I cite Green's theorem twice. Let's see here. So Green's theorem applied to the boundary of D1 gives me a double integral over D1. Green's theorem applied to the boundary of D2 gives me a double integral of D2. Now, of course, that minus sign comes along for the ride, right? But we've already factored out that minus sign. This integral just says boundary of D2. So Green's theorem gives me a double integral on D2. Is that cool? Everybody with me? So again, I've got to, compute appropriately. And let's see here. For this vector field, you compute the curl. And the curl ends up being very nice. It's just 9. It's just arithmetic. Well, partial derivative and a little bit of arithmetic. And so again, we've transformed the question. So let's again try to decide, was this a helpful construction? Would I rather compute 4 separate line integrals like so? Or would I rather compute, I'm going to say 2 double integrals? But in fact, I don't even need to compute the 2 double integrals. I just need to compute the difference of the 2 double integrals. And then you look at the picture and realize D1 and D2 have the same area. These integrals have the same integrand. I don't even need to know what that integral is. The difference is clearly visible. Right? So was that a win? Yeah, I think it was a massive win. Yes?
Would you be able to cite symmetry on this question?
No, for couple of reasons. First of all, let's see. So the main point is that we don't have any symmetry theorems for vector line integrals. So that'd be my first observation. Down here we have 2 separate integrals. And then we also don't really need to invoke symmetry because, well, first of all, it'd be trouble to talk about reflection over a point that a line that's not an axis. And so it'd be more trouble than it's worth, and these integrals are just easy as it is anyway. Is that cool? Yeah. Okay, so another nice use of Green's theorem. All right, now this is a weird one, and it has its uses. This comes up sometimes. Mostly it's a cute curiosity. Here's Green's theorem. Boundary line integral, double integral of curl, right? That's just Green's theorem. Now you will notice though that I am applying Green's theorem here to a very particular vector field. I'm applying Green's theorem here to the vector field 0, x. It's very important. In this conversation here, I only want to talk about the vector field 0, x. And 0, x is special. It's not uniquely special, but it is special in the following way. 0, x has the feature that its curl is just 1. Easy little calculation, right? So think that through, right? dq dx minus dp dy, it gives you 1. Now, why does that matter? Well, if again, we have Green's theorem there, and I've rewritten the curl now as 1, and oh my gosh, now I'm looking at the integral of 1. That gives me the area of my domain. So what's kind of wild is, again, you set this up in just the right way. We have a vector line integral that will compute the area that it's going around. Isn't that weird? Right? It's pretty unexpected that a vector line integral would compute the area inside of it. But it follows immediately here from Green's theorem. Is everybody with me? Special vector field. Now, I should point out, just to be clear, again, it's not uniquely special. There are many vector fields that have this property. Negative y, 0 works just fine. Sometimes it's useful to use, weirdly, negative y over 2, x over 2. Also works, right? Curl is still 1. So pick your favorite, right? It doesn't matter. Any vector field whose curl is 1, this little theorem will work. Okay, and then real quick, I'll point out that, strange though it may seem, a lot of people like to write this in terms of the corresponding coordinate line integral. And this is a case where I actually kind of like that. I mean, if you look at those 2 options, how would we rather write this? I think there's fewer pen strokes on the left. Weirder though it is very compact. You got to give it that. All right. So I'm going to use this notation here. That said, which would I rather do? Would I rather compute an area? Would I rather do a geometry problem? Or would I rather do a multivariable calculus problem? A lot of people are going to say, you know what? Thanks, but no thanks. I'll do the geometry. Well, here's the problem. Sometimes the geometry looks like that. No right angles in sight. It's all jagged and So I guess I could break this up into a bunch of triangles and, oh my gosh, that's going to be super hard to compute. The geometry, and that's going to be brutal, right? All right, so it turns out that the vector line integral is actually pretty easy to compute. The thing that is going to make this work, we are going to use the fact that when you have a line segment, which of course we do down here, right? This region's boundary is all line segments. On line segments, there is a really handy and compact little formula for how to compute integral x dy. Now, this formula that I've written down here is very specific to that integral x dy. In other words, what I get from using exactly this vector field 0, x, and only the vector field 0, x. And the integral of x dy on a line segment, it's got to be a straight line segment. It's the average value of x times the change in y. Snap arithmetic to compute. So we can put these facts together in this example down here. And so again, I want to compute the area of this nasty polygon. Oh my gosh. Okay, well, I tell you what, let's compute on this line segment first. The x coordinates down here, let's see if I can get these. The x coordinates down here are 1 and 12, so the average value of x is 13/2. The change in y, how much does y change? Well, y goes from 1 to 6, so the change in y is 5. So x bar was easy to compute, delta y was easy to compute. Multiplying x bar times delta y is easy to compute. Right? That line integral on that line segment, computed by that formula, is just the product of those numbers, which is that. Simple arithmetic. Now, of course, now we're not done, right? That only does that one line segment. And so, okay, well, then, yeah, you do have to, take this calculation and do the analogous thing now for that edge, which will give you that. And that edge, which will give you that. And et cetera, right? So you do have to do, what's this, 9, I think it's 9 line segments. And so there is some arithmetic to be done, but look how easy the arithmetic is. It's simple arithmetic, right? And boom, I get an answer, and I didn't have to do nasty geometry problems. Again, I could break this up into half a dozen little non-right triangles and try to remember what was that Heron's formula from high school geometry that involves square roots, and it's a very weird formula, right? So much easier. Is that cool? Can I have a cool example? Okay, next example. This is it's going to come off as kind of a different question, and it is a different question, but it's going to turn out to be surprisingly similar. We're going to talk about flux again, and I'm sure y'all remember flux. We talked about flux through a surface, and this is going to be similar to flux through a surface, but we're just going to talk about flux through a curve. So this is kind of the two-dimensional version of what we talked about back in chapter 3. If I'm stuck in 2 dimensions here, and if there's a 2-dimensional fluid moving, and if I want to keep track of how the fluid, this 2-dimensional fluid, is crossing, well, I can't talk about it crossing a surface. There are no surfaces sitting inside of 2 dimensions. 2-dimensional fluids, I would imagine, going across curves. Right? And just a reminder, here's an example of a 2-dimensional fluid that I talked about before. This is just an example, but I like to think of migratory patterns of animals, like herd-type animals, herd, flock, whatever type animals. So if there's, a bunch of zebras migrate, I don't know if they migrate, but whatever. But if there's a bunch of, some sort of migratory birds cruising along, right? I could be interested in, okay, maybe this is the edge of some sort of a national park. And I want to know how many, okay, given how they're migrating and which direction they're going and the angle of the border, etc., how many birds per unit time are crossing out of the national park? Right? So that's a natural such situation. So how do we compute it? This is a nice exercise. I want to encourage everybody to give this a try. This is the formula to compute that flow rate. How much of the fluid, birds, how much of the fluid per unit time is crossing over that curve? So what I would like for y'all to do, and again, optional, but encouraged exercise, go back to chapter 3. Look at the computation that we did for a three-dimensional fluid flowing through a surface and kind of adapt accordingly to this two-dimensional picture. I think you can come up with that as the answer. As always, if you get stuck on this, you're not sure how to proceed, not sure how to get started, whatever the case may be, feel free to come talk to me in office hours. Happy to walk you through it. Be a good exercise. Okay, fine. So now this formula here is when you're talking about flux through just a single line segment. We're going to ask now, what if you have the boundary of a region, right? So maybe I've got some region here, and I want to talk about the boundary, right? To what extent is, I've got this boundary curve, and of course boundaries are oriented a certain way, region on the left. And how many birds are flying across the entire boundary? Right? Well, we need another convention. In this context, when you're talking about flux, when you're interested in a convention on the direction through a boundary, not along a boundary, the convention is that the orientation is outward. Now again, it's just a convention. It's an arbitrary convention. Somebody made a choice a long time ago. There may have even been a convenient motivation to want to make this choice, but it doesn't matter because that's the convention, and we got to get on board with what planet Earth does, and arbitrary but not optional. Does that make sense? Is everybody happy with that? This is just a standard convention. Okay, so that's what we're going to be interested in doing. Before I write it down, and the calculation goes pretty nicely, but I am going to make an observation, and that is that if you're looking at a normal vector dot a field vector, let me get my colors straight. Normal vector dot a field vector, f dot n, that I'm going to be interested in here. If I want to compute that dot product, here's a clever observation. Clever observation is, how about this? Let's take these two vectors. Let's take both of these two vectors and just rotate both of them 90 degrees counterclockwise. Now, I geometric appeal, if I take two vectors and rotate 90 degrees counterclockwise, the magnitudes don't change. The angle between them doesn't change. So the dot product doesn't change. So in particular, if I look at not n, but t. T is what you get when you rotate n counterclockwise. And not f, but f perp, what I'm calling f perp. Again, the result of rotating f counterclockwise. Negative q comma p. Make sure you're clear on why it's negative q comma p. It's a flashback to linear algebra. Again, remember, rotations are linear transformations, which are performed by matrices. The columns are the images of standard basic vectors, all that jazz, right? 90 degrees counterclockwise rotation of PQ will give you minus Q comma P. Come talk to me if you're not clear on why that is. Then this dot product, let's see here. Ooh, color choices. F perp dot T. Yeah. Will give you the same thing. That's just a little algebraic observation, but kind of geometric and algebraic. Okay, so with that observed, here's how we do the calculation. There's nothing to it. If you want to compute the total flux, we'll look at each little piece of flux. Each little piece of flux, we already have a formula. F dot n times the length of a little piece of curve from the previous page. That's how you compute flux through a little straight line segment. And then we use this fact that F dot n is F perp dot T. And then we look at this integral and say, oh my gosh, check it out, T ds, that's dr. And then we say, oh my gosh, look at this. This is literally a good old-fashioned, regular old vector line integral. Right? Integral of a vector field dot dr. We already know how to compute these. You can pull back through a parameterization. You can use fancy theorems if you have them. We have Green's theorem, right? So this is a good old regular vector line integral. Yeah.
How do you know TDS is DR?
That's from chapter 3, way back. Yeah. So if you look at the very first, the top of the first page of the lecture notes on section 3.2, I'm 90% sure it's section 3.2. Yeah. So now we just cite Green's theorem and it's all over but the shouting. Here's Green's theorem. If you want to compute a vector line integral around a boundary, which we are going around a boundary, then double integral over the interior of curl, and then you just have to compute the curl. Now, the curl, you got to be careful. The formula for curl, people like to memorize dq dx minus dp dy. Remember, what's important is not the letters of the alphabet, right? So let me go back a couple of pages here. It's not about the, let's see, where am I? The q here, it's not because it's called q. It's the second coordinate of that field vector, right? And the p here, it's not because it's called p, it's because it's the first coordinate of the field vector. So let's be very, very careful about that. And with that in mind, here we go. Okay, let's see, hang on. Here we go. If I want to compute curl, we're going to look at the second coordinate, x partial, minus the first coordinate, y partial. So that's how curl is computed for negative q comma p. And then having written that down, there's a couple of minus signs to pay attention to. These minus signs here cancel, and this, what had been curl of f perp now just becomes, oh my gosh, we recognize that formula, it's divergence. And again, flashbacks to chapter 3. Right? In chapter 3, I presented that there is this thing called divergence, and I claimed that it's useful for stuff, and that it's about how the fluid is kind of flowing generally outward. And again, if you look at what we've just computed, this now makes sense. Let me come back up to here. We were computing outward flux. We were computing, we were looking at a boundary curve. We were looking at how the fluid flows outward through that boundary curve. And the answer is divergence. Double integral of divergence. But divergence therefore tells you per unit area, and locally, looking one little piece at a time, divergence tells you to what extent are you seeing an outward flow. That's another sort of connection back to chapter 3 that we resolved. Is that cool? Nice easy example here. If you want to compute an outward-oriented boundary flux like that, got a curve, unit circle, going outward, got a vector field given. Now you can brute force this if you want, right? Plug and chug, but again, cosecant, really? Do we want to deal with cosecant? I don't want to deal with cosecant, right? So the alternative is we cite the theorem that we just proved, the two-dimensional divergence theorem. You notice that the divergence of this vector field, the divergence is just minus 3 Again, super easy integral, victory, no dealing with cosecant. Y'all have a good rest of your day. See you later.